Hello students, how are you? Doing well? Very good. Dear students, we have been learning HaloAlkanes and HaloArenes. Under this chapter, we have completed their preparation, physical and chemical properties of HaloAlkanes. Today, we are going to learn HaloArenes, chemical reactions and their properties. Dear students, usually HaloArenes undergoes electrophilic substitution reactions. Yes students, usually haloarenes undergoes electrophilic substitution reactions. They are commonly halogenation, nitration and sulfonation, Friedel reaction, which is alkylation as well as acylation. Whereas nucleophilic substitution reactions of these compounds are very rare and it undergoes under few reaction conditions, under very specific reaction conditions. We will learn very few reactions under these nucleophilic substitution reactions. However, electrophilic substitution reactions are common with respect to haloarenes. And the third category of reactions haloarenes undergoes are reaction with metals. Under this, we are going to learn about Wurtz-Fittig reaction and Fittig reaction. And after this, we are going to focus on polyhalogen compounds, that is the compounds which are having halogens, for example dichloromethane, chloroform, iodoform, freons and DDT. Yes students, let us see the chemical properties of haloarenes. Yes, let us take chlorobenzene. This is the chlorobenzene, right? So nucleophilic substitution, is it easy to undergo nucleophilic substitution of this chlorobenzene? This is having, yes, chlorine is a negative inductive minus I affecting group, that means it pulls the electron density towards this side, one thing. And however, the second factor and important factor of this chlorine is it also has lone pair of electrons which resonantly stabilized, or it mesomeric effect of these two electrons or this lone pair of electrons, it resonantly stabilizes with ring, that means it back donates towards ring and it is going to form nucleophile at ortho position, and further resonance it is going to form nucleophile at para position. So haloarenes forms nucleophilic positions at ortho and para, that means the haloarenes are ortho para directing groups, right? So though it is having negative inductive affecting nature, however the positive nature, this mesomeric effect is more stabilized by resonance effect. So it is not easy to remove this double bond by substitution, nucleophilic substitution. It is not going to take place with respect to haloarenes, right? So this is how ortho and para positions are going to be directing groups. So difference in hybridization of carbon atom in CX, whereas CX, that is haloalkanes, this is haloalkane, right? So when it comes to haloalkane, we have seen that nucleophilic substitution SN1 and SN2, whereas aromatic halo compounds, it is not possible or it is tough to undergo aromatic nucleophilic substitution. Why? Because the CX bond or the bond between carbon and halogen is sp3 hybridized carbon. That means the electronegativity compared to this sp2 hybridized carbon is less. And in this haloarenes, the bond is, the carbon is sp2 hybridized. So the sp character is about 33%. Because of this 33% of S character, it is highly electron negative character is more when it compared to sp3 hybridized carbon. So it is not easy to break this double bond type of character, or it is not easy to undergo nucleophilic substitution. an instability phenyl cation. Imagine somehow it forms phenyl carbocation. This is phenyl carbocation. Is it stable? This is phenyl carbocation. Is it stable? No, because it is not aromatic. It is not aromatic. So it is not going to be stabilized. So because of instability of phenyl cation and difference in hybridization of carbon atom in CX bond and resonance effect, these haloarenes usually do not undergo nucleophilic substitution, and because of the possible repulsion, right? So when some nucleophile wants to attack this carbon, this is nucleophilic substitution, where if someone wants to substitute this chlorine atom with nucleophile, and the incoming nucleophile also will have electron pair. So this electron pair is going to repel. That is why nucleophilic substitution is not observed in haloarenes. But however, we come across few reactions. For example, replacement by hydroxyl group, where treatment of this chlorobenzene with sodium hydroxide at high temperature under pressure. See, 300 atmosphere. Usually what is the atmospheric pressure at room temperature? It is 1. So you are forcibly making to undergo nucleophilic substitution. That means the incoming nucleophile is OH minus is forcibly replacing this chlorine is tightly attached to arene carbon. However, this OH minus is replacing at high temperature under high pressures. However, so to make it possible at a low temperature, yes, when the halogen compound or this haloarenes are substituted with nitro group, either ortho or para, it is going to undergo this nucleophilic substitution very easily. For example, it is substituted at para position, say 443 K, means it is around, if I remove 300, it is around 150 degrees centigrade. So doing 150 degrees centigrade reactions at room temperature is common, right? So at laboratory level we can do it. And when it comes to substitute with two nitro groups, especially at ortho and para, it is going to be very easily removable or substitutable with nucleophile of OH minus. See, 368. So what is the temperature? It is less than 0 degrees centigrade. So at room temperature, below the room temperature itself, this compound is undergoing nucleophilic substitution. And when this is substituted with 3 positions, dear students, the key factor I would like to say here. So when ortho para is substituted, it is requiring some temperature, or say 368 K, right? So some temperature is requiring. When it is substituted more number of these nitro groups, just warm means just 40 degrees is enough to undergo this reaction to nucleophilic substitution. Then why? What is happening? So just now what I said, nucleophilic substitution is usually not possible, but when the ring is substituted with nitro group, it is easily allowing the incoming nucleophile to substitute chlorine group. Then why it is happening? Let us see. So if you take this chloro compound, when it is substituted with the nitro group at ortho position, the incoming nucleophile, this is a hydroxy group, easily replaces this chlorine. Chlorine is going out. Why? Because the incoming nucleophile is going to form nucleophile or anion at this negative charge at this ortho position, which is attached to nitrogen. This nitrogen or this nitro group is going to be stabilized this negative charge by pulling this negative charge into this carbon or into this oxygen. So nitro group is going to stabilize this anion which is formed during the nucleophilic substitution with sodium hydroxide or hydroxyl group. So that is why, so if you write the resonance structures of these compounds, what is happening? It is going to form ortho and para. So since it is substituted at ortho position nitro group, it is easily replacing or substituting hydroxy group with chlorine group with hydroxy group. Yes, When it is para, same thing is going to happen. What is happening? The negative charge which is formed here, it is going to be stabilized. So this nitro group stabilizes like this. Yes, you can write the structure like this also. So it is going to form double bond here and double bond. It is stable. Yes, so because of this stabilization, the chlorine is easily substituted with hydroxy group. The same thing when it comes to meta position. So during the resonance stabilization, it is not going to form negative charge at meta position. Do you observe negative charge at meta position? This is meta position, no negative charge. In all resonance forms there is no negative charge. So this nitro, though it is having nitro substitution at meta position, it is not going to have any effect. So nucleophilic substitution of meta substituted nitro compound is very tough, student. And moreover, not only this nucleophilic substitution, there is a common trend, that is ortho effect. Ortho effect, if it is simple, even if you take nitrobenzene, it is irrelevant at this point, but time has come, I would like to explain. When you discuss about nitrobenzene, the hydrogen which is ortho to nitro group is easily substitutable by nucleophile, because it is acidic proton type. It is acidic type proton. That I will explain when I am teaching about nitrobenzenes, nitro compounds. Anyhow, so this is how it is going to favor the nucleophilic substitution reaction on aromatic arenes. Yes, students. So the common reactions what we observe, electrophilic substitution reactions of haloarenes, it is halogenation, nitration, sulfonation and Friedel reactions. Yes. So the orientation of haloarenes is ortho and para. How? See, let us see. So because of this lone pair electron, it is going to resonantly stabilize and it is going to form ortho position negative charge. So it is negative charge, and the incoming reagent what it should be? It should be electrophile. Right? So electrophile, because it is having electron excess, so it wants to react with electrophile. It wants to give this negative charge to electrophile, which is electron loving species. So it reacts with electrophile and forms ortho and para. Yes. So then what is going to happen? What is the orientation? So haloarenes are ortho and para directing groups. Yes. So when you do the halogenation with chlorine and anhydrous ferric chloride, so what is going to happen? It undergoes aromatic halogenation. Yes. What is happening? It is going to give two products, mixture of two products. What is this? One is monochloro, that is ortho-chloro, chlorobenzene. It is para-chloro-chlorobenzene. R14 dichlorobenzene and 12 dichlorobenzene. So here it is written as para is major and ortho is minor. Why? It is very simple, students. So since it is a chlorine group, when the incoming chlorine, so this is chlorine. If the incoming chlorine, what should be the charge on chlorine? It is positively charged, right? So what is happening? Chlorine in presence of Cl2, in presence of ferric chloride or aluminum chloride, is going to form ferric chloride. Aluminum chloride, it's a Lewis acid. It takes up this ferric chloride Cl4 minus. It forms ferric chloride Cl4 minus, and the incoming electrophile this is, and already this bulk group of chlorine, when it wants to come at ortho position, there will be repulsion. Since it is a big group or chlorine group or halogen group is already there. So though it is facilitating the ortho position, so the incoming chlorine group, it is very tough to approach the ortho carbon. That is why though it is forming, it is minor compound. Minor means you are getting very few percentage of ortho product, but the para position, yes, it can attack very easily. This carbon is very easy to attack. So para chloro dichloro compound we are going to get. Same thing holds good when it comes to nitration. Nitration also. Yes students, so major what is going to form? Para nitro, because the incoming nitro group, what is the electrophile here? Nitro group. Yes, in previous lesson HaloArkanes, hydrocarbons, aromatic hydrocarbons, I have explained nitration reaction. NO2 plus, it is going to be formed from HNO3 plus H2SO4 sulfuric acid. So the incoming electrophile, this easily attacks onto ortho position and para position. Para is major because the nitro group is very bulky group. Already chlorine is here. When it wants to come, it is tough, though it is forming, facilitating the entry. But this chlorine group which is there already, it is not going to allow because of this repulsion. It is repulsion. So there will be tough to approach here. Whereas this para position, it is free to enter. That is why the formation of para compound is major. Yes students, and here I want to ask a question. Suppose if I want to make this para nitrochlorobenzene, it was asked in 2020 NEET. Yes, so if I want to make this para nitrochlorobenzene, from benzene, what is the route you propose? From benzene to para nitrobenzene, para nitrochlorobenzene, what do you do? If I make nitrobenzene first, if I make nitrobenzene here, let me write nitrobenzene, what is going to happen? Yes, nitration, I can do nitration, I am going to get nitrobenzene. Yes, nitrobenzene I am going to get. Nitration HNO3, H2SO4. So nitrobenzene is formed. So nitrobenzene, when I want to do chlorination, yes, chlorination, I can take chlorine in ferrichloride, chlorine, iron chloride. So what is going to happen? This nitro group is meta-directing group, but when you are required is with para-chloro-nitrobenzene, then what will you do? So you are going to get meta-chloro. So if you are asked to make this from benzene, it is the way to make is first make benzene to chlorobenzene, this chlorobenzene, by simple chlorination. In presence of iron chloride, you are going to get chlorobenzene. This chlorobenzene upon nitration, you are going to get this para-nitro. Whether it is bromo, it can be bromo, it can be iodo. Yes, doesn't matter. These chloro, bromo, iodo compounds are ortho-para directing groups. That is how you can make this halogen substituted nitro compounds. Sulfonation, so same thing, sulfonation also, it is also electrophilic substitution reaction, where it is going to, so it is concentrated sulfuric acid is given, but it should be oleum, fuming sulfuric acid, oleum. Yes students, so oleum is going to undergo sulfonation. Na2S2O7 or H2S2O7 is oleum. This oleum mixture, fuming sulfuric acid, is going to undergo this sulfonation. Usually concentrated sulfuric acid, even if you heat for at high temperature, it is not easy to undergo this sulfonic compound. These sulfonic compounds are like char-like compounds, right? So what is happening here? Also para position is going to be major product. Yes students, so electrophilic substitution, sulfonation is completed. Then Friedel-Crafts reaction, and moreover, so whatever may be the electrophilic reaction, what are the steps involved? There it will involve 3 steps. What is the 3 steps? So let me write this for 3 steps. Electrophilic substitution 3 steps. Usually it follows generation of electrophile. So this chloromethane plus anhydrous aluminum chloride, it is going to form generation of methyl cation. This is electrophile, generation of electrophile. Yes, and aluminum chloride is going to be AlCl4. So this is the first step, and the second step is generation of intermediate, where it is going to transition state is going to be like this. Let me write at ortho position. So this is going to attack onto this methyl group to give chloro here, and here already is here one hydrogen will be there, and it is attached to methyl group. Yes, so this is intermediate, where if I want to write the resonance structures, what is going to happen? Yes, so this is a transition state where you will find, so this is carbocation, isn't it? So carbocation is stabilized by this lone pair of electrons. So I can stabilize or resonance this side, or this side. Wherever I want, I can put this 2, 1, 2, 3, 4, 5. 5 carbons are going to share this carbocation, this positive charge. So transition carbocation intermediate. Then what is the third stage? So removal of hydrogen. Removal of hydrogen to give product. In this case, it is going to give chloro. So it is, because of this aromatic nature, it is going to lose H plus or H hydrogen ion to give methyl. So this is how all free electrophilic substitution reactions involves generation of carbocation and transition state and removal of hydrogen, whether it is chlorination, nitration, sulfonation or Friedel-Crafts reaction. So that I have explained in detail during aromatic hydrocarbons. Anyhow, so this is Friedel-Crafts alkylation. Here also what is happening? So para is going to be major, right? So major is para. So when it comes to acylation, so acylation also is going to take place. The carbocation is acylium ion, acylium carbocation or acylium ion. So this chlorine is going to out, and it is going to react this double bond. It is going to give ortho and para, and here also para is major. Then how will you separate these two compounds? Do you have any idea? Usually these ortho compounds are steam volatile. Ortho compounds are usually steam volatile, and because of this hydrogen type bonding, so this is oxygen and chlorine, it is going to form this hook like bonding, and it is going to have low boiling point, and it is going to form steam with water. It is going to form hydrogen bonding, so it is easily removed at a low temperature. And whereas this para-estophenone, parachloroestophenone remains in the reaction vessel, or it can be distilled after the distillation of these two compounds. Yes, students, so this is all practical problems, don't worry. So the important thing to catch here is just concentrate why major para is going to major. What is the reason? Because the incoming repulsion between this acyl group at ortho position and chlorine. When it comes to para position, it is easy to approach para position. That is why it is giving para acetyl chlorobenzene. Yes, so this is para-chloroacetophenone. These compounds are acetophenones. Yes, students, so this is how you can make electrophilic substitution of aromatic halo compounds. Next, let me ask questions. Although chlorine is an electron withdrawing group, just now I have explained withdrawing group, yet it is ortho and para directing group. Electron withdrawing group, for example, if I take nitro compound, nitrobenzene, what is the orientation of nitrobenzene? It is meta directing group. So the electrophilic substitution takes place at meta position. So they are asking, so it is also like electron withdrawing group. Yes, electron withdrawing group chlorine. However, it is undergoing electrophilic substitution and it is directing ortho-para contrary to its electronegativity. The reason is, though it is electron withdrawing group like this, it is pulling the electron density of benzene ring towards it, but the resonance stabilization or back donation of this lone pair electrons is major, right? Attack at ortho position is stabilized by back donation of this lone pair of electrons, right, attack at para position and ortho position is facilitated by this resonance stabilization because of mesomeric effect of this. So what is going to happen? Though inductive effect is destabilize the intermediate, carbocation formed during the electrophile substitution is going to be stabilized by its lone pair of electrons. That is why it undergoes electrophilic substitution and it directs the incoming electrophiles at ortho and para. Yes, students. So this question you will get a number of times. Yes, when it comes to practical problems, if the compound is having this nitro, for example, it is having nitro. So nitrobenzene, when I do chlorination, it is going to go give this. Yes, so this meta nitrochlorobenzene, if I do nitration, where it undergoes. So this type of mixture of compounds we are going to get. If I want to do chlorination here also, what is the product where it is going to undergo? So if I do chlorination of this compound, it has three positions. This is ortho, this is ortho, this is ortho, this is para to chlorine, and this is ortho. So which is easy to undergo chlorination? In this case, is it easy to undergo this position? No, this nitro group is very bulky group. At the same time, it is going to direct towards its meta position. So because of this nitro meta position, instead of going this chlorine effect, chlorination takes place at this position and it can form some mixture at this position. So the probability is 1 and 2, where this position is free with respect to chlorine, and though it is ortho, it is going to form at this position. So these are all practical problems. So orientation is very important when it comes to synthetic organic chemistry, right? So that is why nitro group, when you find a nitro group withdrawing group, it is meta directing group. So please remember, nitrobenzene, when you do the nitration, electrophilic substitution, it is going to form meta dinitrobenzene. Yes, so based on that, entire chemistry depends. So remaining, when it is electron donating or activating groups like phenol, it is going to form electrophilic substitution reactions, and that is ortho and para. Next, and HaloArenes, what I said, the third category of reactions HaloArenes undergoes are Wurtz-Fittig reaction, and this is nowadays we are not doing, though it is very important to do. Alkyl halides, sodium and aromatic halides in presence of dry ether, what is going to happen? It is going to take out this halogen and this sodium with this halogen. It is going to be out as it should be 2Na, right? 2Na, one is green X and other one is this black color X. So 2Na(X2) is going to out, and it is going to give aryl compounds or alkylated aryl compounds. Yes, so the yields are very poor with respect to this reaction, because there is a chance to undergo self-Wurtz reaction, because this alkyl halides self-coupling takes place to give alkane, and there is a chance to form diphenyls also, diphenyls like this. So it is a mixture of three products we are going to get Wurtz-Fittig reaction. To overcome this, so there is a way to make these compounds is Fittig reaction, where you can take only aromatic halides, and when you do the sodium reaction in dry ether, it is going to give diphenyls. So this is very important reaction in organic chemistry, where you can prepare diphenyls. Yes, students, so this is how it is. Aromatic arenes are going to undergo this Fittig reaction. Yes, students. So which alkyl halide from the following pairs would you expect to react more rapidly by ascent mechanism? Explain your answer. Yes, students. So this is aliphatic alkyl compounds. So this HaloAlkanes, yesterday in previous lecture I explained that SN2 reaction. So let me write again, SN2, this is SN2 and this side SN1. So SN1 is favorable in tertiary alkyl halides, whereas SN2 is favorable in primary alkyl halides. Yes students, so what is the question? SN2, they are asking SN2. So explain, you expect react more rapidly by SN2. So the compound, this is SN2, so the primary alkyl halide going to react more fast, and here this is not at all undergoes SN2, it undergoes SN1, right? So this is, though it is secondary, there is a chance to undergo SN2 reaction. When it comes to this, so though it is primary and it is also primary, but it is when you look from this side, it is very near to this secondary carbon. So this is going to undergo SN2 very easily when it compared to this compound. So this is how SN1, SN2 in previous lesson I have explained, right? In the following pairs of halogen compounds, which compound undergoes faster SN1 reaction? Just now what I said, SN1 reaction, tertiary alkyl halides easily undergoes tertiary alkyl halides. So this is easily undergoes. When it comes to this, it is going to be SN1 secondary alkyl halides when compared to primary alkyl halide. SN1 takes place. Then, so this is very important students. Find A, B, C, D, E, R, R prime. So this type of questions you are usually going to get in board exams as well as in NEET and JEE or whatever may be the entrance exams. So don't worry, just now what I said. So alkyl halide, when you treat it with magnesium in dry ether, what is this A? You are going to get Grignard reagent, organometallic compound, alkyl magnesium halides or aryl magnesium halides are known to be Grignard reagents compound. Yes, so this Grignard reagent, when you treat it with water, it is going to form hydrocarbon or alkane, cycloalkane. So it is a common side reaction. If you have any moisture or air or water, so this reaction or Grignard reaction is going to spoil and it is going to release this alkane or aromatic this hydrocarbon. That is why Grignard reaction must be done under extreme dry conditions. Yes students. Next, so same reaction, alkyl halide in presence of magnesium, when you treat it with dry ether, it is going to form alkyl magnesium halide. This alkyl magnesium halide, when you treat it with deuterated water, D2O, you are going to get deuterated product. Yes student. So they have given this two position. Yes, two deuterated propane. So they are asking what is R. So R is, so this is CH2 or CH3. I can write, yes, it is already here. So CH3 CH, it is bromo here. So it is going to form alkyl magnesium halide, and this alkyl magnesium halide, it is going to give deuterated compound. This is one of the ways to prepare deuterated alkanes. Deuterated alkanes are very important compounds even in NMR, because deuterated compounds are used as organic solvents in NMR spectroscopy to dissolve the organic compound. So this is one of the ways to make deuterated compound. CdCl3 deuterated chloroform we use commonly in proton NMR, right? So this is what is happening. This is R prime X. When you do sodium ether, what is the reaction? Wurtz-Fittig reaction. Wurtz reaction, you are going to alkane. So in 2020 NEET it is asked. So is it easy to make odd number carbon containing alkanes by Wurtz reaction? No, because it is going to form dimer of, even if I take mono or one alkyl or ethyl chloride or butyl bromide or whatever with the compound, odd plus odd also gives even number of carbons, and odd plus even carbon containing halogens also going to give even number of carbons. So the answer is odd number containing carbon containing compounds by Wurtz reaction is not going to be prepared or not going to be formed. So here what is the reaction? So please concentrate, students. Here what they have taken, though it is tertiary alkyl halide, it is going to undergo Wood's reaction. This is tertiary alkyl halide, tertiary butyl. If it is bromo, it is tertiary butyl bromide. It is undergoing this Wood's reaction to give this product. When you treat it with magnesium, yes, this is also tertiary butyl magnesium halide is going to be formed, and this upon hydrolysis you are going to get tertiary butane. Yes, so this is what some of the questions. And when it comes to polyhalogen compounds or halogen containing compounds, the common compound in laboratory you will come across is dichloromethane. Dichloromethane is used as a solvent in organic chemistry. Nowadays it is banned in so many countries. When if you go to Japan, it is very tough to find this dichloromethane, or you are not at all going to be allowed to use this dichloromethane in laboratory. But previously it was used extremely in organic synthesis as a common solvent. Why? Because it harms human central nervous system, impaired hearing and vision, and it may cause dizziness, nausea, numbness. These are all the problems. And burning and mild redness of the eyes can burn the cornea. If a drop also falls onto your eyes, it is going to burn your cornea. That is why this dichloromethane previously was used very abundantly. However, still in India also we are not using, but just before 10 years back it was used commonly as organic solvent to extract and the reactant solvent. For example, during the halogenation, so many reactions you will come across in dichloromethane as a solvent. Yes, students, this is synthetic solvent, right? So when it comes to chloroform also previously used abundantly as a solvent in organic chemistry, but now it is also banned and it is rarely used. And moreover, as a solvent, previously it was used as anesthetic compound. Chloroform, anesthetic, you might have seen in some movies, they do some spray of this chloroform and they kidnap, while kidnapping some villain or something, they use chloroform. But now it is not available and it is not that effective. So in movies they have usually come across this chloroform actions, but it is not going to affect that fastly. However, for long exposure to this chloroform, it can cause dizziness, fatigue and headache. However, why it is banned? Because the chloroform which is there is going to react with oxygen in presence of light. It is going to form highly poisonous compound phosgene. This phosgene is very highly poisonous gas. So this poisonous gas is going to make you die, right? So because of this poisonous gas formation with chloroform, it is banned, right? So this is one of the very important point to remember. So it forms phosgene. Chloroform forms phosgene. So please remember, this chloroform is going to react with oxygen and forms phosgene, which is highly poisonous. And to overcome this type of reactions, in presence of light only this reaction takes place. So that is why this compound or chloroform is supplied in colored amber color bottles in organic synthetic laboratory. Yes, students. So this is our trichloromethane or chloroform. And triiodomethane or iodoform, previously it was used as antiseptic, but nowadays it is not used because advanced better compounds are available. Yes. So when it was observed that the free iodine which is come out from this iodoform is going to act as antiseptic, so instead of using this, povidone iodine is used. Povidone iodine is used as antiseptic nowadays. So this iodoform is not going to be used nowadays because objectionable smell, and it has been replaced by other formulations containing iodine, right? When it comes to tetrachloromethane, carbon tetrachloride also is very common solvent in organic chemistry. Bromine in CCl4. Yes. So CCl4 is used as common solvent, but because of its side effects, nowadays this CCl4 also banned. So unless it is very essential to use this carbon tetrachloride in organic reaction, then only you are allowed to use this carbon tetrachloride in organic chemistry. However, previous to this, it is used huge amount for the preparation of refrigerants, freons, and general organic solvent and cleansing fluid, and even it was allowed to use as fire extinguisher at home. But when it is found that it is going to cause liver cancer in humans, dizziness, light headache, nausea, vomiting, damage to nerve cells, stupor, coma, unconsciousness and death, so it is removed. Then what is the major factor to remove this solvent from organic chemistry lab is it depletes the ozone layer. When it goes out into atmosphere, it is going to deplete the ozone layer. What happens if it depletes ozone layer? Yes students, I am concentrating these points because you are going to be asked, is it carbon tetrachloride is going to cause any effect on ozone layer? Yes, it causes. So exposure to what happens if depletion of ozone layer takes place? Exposure of ultraviolet rays takes place. So that ultraviolet rays are going to be lead to increased skin cancer, eye disease, disorders, and possible disruption of the eye and immune system. And freons. So freons are highly objectionable compounds, where these freons, when it goes into stratosphere, and these upset the natural ozone balance. So these freons are very highly objectionable compounds, which are halogen compounds, but these are very, very important compounds where their utility comes at, it is usually used as industrial use, as common industrial, as aerosol propellants, refrigeration, air conditioning. Yes, so though they are very highly useful, so the care must be taken to use these compounds. And let me take this Schwarz reaction. What is Schwarz reaction? Yesterday I explained. So preparation of fluoro compounds from halogenated compounds. So if I take this tetrachloromethane, if I use iodine, it is going to be Finkelstein reaction, but fluorine compounds are not going to undergo Finkelstein reaction. Then how to make this fluoro compound? So simply treat it with silver fluoride. Silver fluoride, when you do silver fluoride reaction with silver fluoride, this reaction is known as Schwarz reaction. So by Schwarz reaction you are going to make freons. So freons, usually this is a structure, but it is a mixture of methane and ethane, collectively known as freons. So ethyl, dichloro, difluoro. So mixture of fluoro and chloro compounds are known to be freons, and these freons are highly objectionable compounds, are highly toxic compounds when it goes out into atmosphere. Yes students, right. So the important first compound, which was, yes, at the beginning of this lesson I explained what are the drugs of having chlorine or halogen compounds. For example, I have given examples of chloroquine, right, chloramphenicol, thyroxine, so halothane. They are all drugs. Yes, so they are all drugs and used for the treatment of various diseases, like chloroquine is for malaria treatment, right? So chloramphenicol for the treatment of typhoid, like that. And haloform is for the anesthesia, thyroxine for goiter, like that. However, there is an antiseptic compound which is DDT. So the common name is DDT, which is nothing but para. This is para position. With respect to this is para position. Para dichloro diphenyl, because this is diphenyl. Trichloroethane, trichloroethane is DDT. It is commonly used as insecticide, where it kills or it repels mosquitoes and lice that carry typhus. So typhoid fever during the Second World War, it was a pandemic, like nowadays what is happening corona case with respect to corona. So during 1950s, like that, during those days, and malaria and typhoid killed a lot of killed a lot of people. So because of this DDT, it was come under control. That is why the Muller, who found this DDT or who prepared at this Geigy company, pharmaceutical, Germany, so he was awarded Nobel Prize. However, slowly what happened? The insects and lice and mosquitoes developed resistance to DDT. Nowadays DDT is not used and other compounds are using. So what is happening? Not only that, it is found that it is the compound DDT is not metabolized when it is sprayed in atmosphere. So what is going to happen? It will be laid on plants and whatever, maybe the grass. So that grass and plants are going to be eaten by animals or even human beings. When it goes inside the animals, so we expect it gets metabolized, but it is not going to be metabolized. Instead, it is going to be deposited and it is going to cause damage to the animals as well as human beings. So that is why it is, moreover, it is banned in United States. However, in India we are using this DDT now, but not that common. Yes, so this is how HaloArenes or HaloAlkanes are very important compounds. Dear students, we have completed HaloAlkanes and HaloArene chapter. So what is the summary of this compound? Alkyl aryl halides may be classified mono, di or polyhalogen, tri. So the first point, tri, tetra, etc. compounds depending on whether they contain 1, 2 or more halogen atoms in their structure. Since halogen atoms are more electronegative than carbon, the carbon-halogen bond alkyl halide is polarized. That also I explained. So this is, so the X, it is polarized. It is going to have partial negative and partial positive charge. Yes, so haloalkanes. The carbon atom bears a partial positive charge, and the halogen atom bears a partial negative charge, isn't it? So this is what we learned. Next, alkyl halides are prepared by, what are the preparation methods? Free radical halogenation of alkanes, addition of halogen acids to alkenes, replacement of hydroxyl group. So what is the common reagent used for the replacement of hydroxyl group? Thionyl chloride, phosphorus halide, thionyl chloride, halogen acids, aryl halides. When it comes to aryl halides are prepared by electrophilic substitution, right? So chlorine in ferrichloride. Fluorides and iodides are best prepared by halogen exchange. What is the reaction? If I want to make iodides, this is Finkelstein reaction. If I want to make fluorides, it is known as Schwarz reaction. The boiling points of organometallic organohalogen compounds are comparatively higher, right? So if I take for example methyl, comparatively higher than the corresponding hydrocarbons. So if I take for example, this is chlorobenzene and this is toluene. So this toluene, when you compare the boiling points of toluene and chlorobenzene boiling point is more greater than this toluene boiling point. So this is the boiling point because it is going to form double bond like character. So it is highly packed and the boiling point is going to be high because of strong dipole and van der Waals forces of attraction. Yes. So even intramolecular and intermolecular van der Waals forces will be highly tightly packed because of these van der Waals bonds, and the boiling points are going to be comparatively high, right? The polarity of carbon halogen bond of alkyl halides are responsible for the nucleophilic substitution. Alkyl halides easily undergoes nucleophilic substitution. What are the nucleophilic substitutions? There are two types. One is SN1 and SN2, and their reaction with metal atoms to form organometallics. What are the organometallic compounds we come across? Grignard reaction and Woods reaction. Nucleophilic substitution reactions are categorized into SN1 and SN2. So dear students, please remember SN2 reactions are observed in tertiary halides and SN1 is observed in SN1 is tertiary and SN2 is primary. And what is going to happen when it comes to aromatic halo compounds? It undergoes aromatic electrophilic substitution. right? On the basis of their kinetic properties, chirality has a product role in understanding the reaction mechanism of SN1 and SN2. What is going to happen in SN1? SN1, we are going to get racemic mixture, racemic mixture we prepared, and SN2, what is going to happen? SN2 is going to undergo Walden inversion, and it is going to give inversion product. If the starting material is positively signed, it is going to give negatively signed compound. Usually it is a case. So inversion is going to take place in SN2, whereas SN1 chirality is going to be racemized mixture, racemic you are going to get. And reactions of chiral alkyl halides are characterized by the inversion of configuration. So this is inversion is taking place with respect to SN2, while SN1 reactions characterized by racemization. A number of polyhalogen compounds, so dichloromethane, I explained, chloroform, these are all solvents. Dichloromethane boiling point is around 40 degrees and chloroform is 60. Iodoform usually we do not use. Carbon tetrachloride is also 64. Freon, DDT, yes. So these are common organic solvents: dichloromethane, chloroform and carbon tetrachloride. If you enter into any synthetic organic chemistry lab, you will find dichloromethane on table, chloroform and carbon tetrachloride. These are commonly used solvents, but nowadays these are banned, though commonly we are using still in India. However, some of these compounds cannot be easily decomposed and even cause depletion of ozone layer and are proving environmental hazards. Yes, students, so this is how aliphatic halo compounds or HaloAlkanes and HaloArenes are going to be very important compounds with respect to your board exams, annual exams and all entrance exams. Dear students, if you have any questions, please comment and don't forget to click on like button and bell button, and please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. We'll meet again with a new topic. And dear students, before this in next video we are going to solve the question answers from this HaloAlkanes and HaloArenes. We'll meet again very soon with exercises based on this HaloAlkanes and HaloArenes. Till then, bye, take care, all the best. Thank you. Arigato gozaimasu. Sayonara. Dear students, arigato gozaimasu means in Japanese it is thank you very much. Yes, so thank you very much. Arigato gozaimasu. Bye. Sayonara. We'll meet again with a new topic, that is exercise from this topic. Bye till then.